All right, so first of all, it's great to be here. Thank you so much for inviting me, and thank you so much for organizing this great conference. So I'm going to talk about the paper that appeared yesterday, and that's work done with our postdoc Andrzej Pokraka, who is here, right there. So he's going to Amsterdam and IS next month. Mark Spradlin, who is also here somewhere in the back, and our second-year graduate student, Hee-Cheng Wang, who is right there. And Hee-Cheng is going to tell you a little bit more, have a little bit more details in his poster with all the letters and everything. So very good. So and the talk title is Symbol Alphabets in QCD. So I'm really proud of having QCD in my title, and flat cluster algebras. All right. So here's the outline of the talk. So I'm going to start with a short advertisement of two papers that I'm not going to talk about. I'm going to have a slide per paper. Just some recent work, a little bit orthogonal to the subject of the talk, but nevertheless, I think it's important to tell you a little bit about it. Then I'm going to have a review of the relation between the symbol alphabet in planar n equals 4 Yang-Mills theory and Grassmannian cluster algebras. So we've heard already a beautiful talk by Ruth yesterday, reviewing some of those things. And then it will be part about our paper, and that would be about the relation between the symbol alphabet and massless QCD. And we did hear a little bit about the symbol in Bayou's talk yesterday, and flat cluster algebra. So I will review. So I'm not going to assume too much. I've been in this field for some number of years, and I see a lot of young people who I don't know. So I'm not going to be assuming too much. I'll just tell you everything you need to know to read our paper, and then I will conclude. So, but before the subject of the talk, I really feel like I should advertise our group. So one slide on on the recent paper with my graduate student who had just graduated, going to UPenn and IIS, Shaunak De, our brilliant new postdoc, Shruti Paranjapi, and Andrzej Pokraka, who's also here, where we investigated hidden zeros of cosmological wave functions. And Andrzej is going to talk about it at the meeting next week. So that's advertisement number one. And then the advertisement number two, that's a work, again, with Shruti Paranjapi and our second-year graduate student, Marcus Skwornik, where we explored large deformations of trace phi cubed theory. So we will hear, I guess, some talks about trace phi cubed at this conference, and I think Song probably gave a series of lectures at the school. So there we explored various deformations and found some shifts which describe some interesting amplitudes. Okay? Boom. All right. So that was 3 minutes, so not too much time off. So now back to the paper. So let me just very, very briefly, some older folks have heard this many, many times and know this very well, but this is not for you. Just a couple slides review on the connection between symbol alphabet in n equals 4 Yang-Mills theory and Grassmannian cluster algebra. So recent, so very, very ancient work. And the main statement is that was suggested in our paper over 10 years ago, is that for the endpoint amplitude in n equals to 4 Yang-Mills theory, the symbol alphabet is described by the Grassmannian cluster algebra GR4n. So that's the main statement that you need to remember. And let me provide some details. So the statement is based on the two-loop observation. So I'm going in historical order because I'm going to be using the same logic and same statements for new alphabets in QCD. So everything will be like, it'll go in parallel. So this observation was based on the following result. So first, the symbol alphabet for 2 loops, 6 and 7 points amplitudes has been worked out in these papers. And the alphabet is given, is there a pointer? Yeah, is given by the set of letters. And for 6 points, it's 15 letters. And for 7 points, it's 49 letters. And so these are all the letters that appear. So that's a result of the calculation that one had to do in n equals to 4 Yang-Mills theory. So once one has the calculation, then one can observe and analyze the mathematical structure. So, and we did observe that these are not some random letters that appear, and they momentarily I will say what they have to do with cluster algebra. But first, I need a refresher. So this is again for younger folks. 3 refreshers you need in order to understand this statement. So number 1, what are the variables? So what are all these brackets? So you are very used to describing the momentum into P, so amplitude-dependent momentum P, in terms of spinning helicity variables lambda and lambda tilde. So now from spinning helicity variables, you go to something called momentum twisters, so these Z's, and then you make the brackets out of, so the brackets on the previous page. I try to make this talk very self-consistent with a minimal detail, but every single necessary detail should be on the slide. So then you go between lambda and z's by this change of variable, and the brackets defined on the previous page are as follows. So that's a refresher. So that shows you what the coordinates are here. That's refresher number 1. Now refresher number 2 is what is the symbol alphabet. So as you heard already from Ruth, the amplitudes are described by certain transcendental functions to some loop order and some number of points. Those transcendental functions obey these recursion relations, and the symbol is defined recursively by formula like that. So for example, for the log, the symbol of log is x, and symbol of Li2 is -1 minus x 10 to x. And it's been 15 years since we've introduced it to amplitudes. And okay, so again, I go back and forth. So we've learned that the symbol alphabet is described by these coordinates. And now the main statement that these are not that alphabet is not something unknown to mathematics. That's actually something very well known, and it's described by the Grassmannian cluster algebra. So I'm going to do a 1-minute refresher on what Grassmannian cluster algebras are. So cluster algebras are defined by 2 things. Number 1, initial seed. So you organize some of your variables into some kind of quiver. So you have variables right here and the quiver. So that's the first thing. And second thing, you need to define, so this quiver, the way the arrows connect those variables, that defines for you something called a mutation rule. And so for this quiver in particular, the mutation rule is a known formula where you just keep track of how the arrows go between the nodes. And so the cluster algebra, a class of variables are as follows. So you have your quiver and you have your mutation rule, and you take each node and you apply to each node mutation rule, and then you get some set of variables. Sometimes it's infinite, sometimes it's finite, but that's what's called cluster variables. Okay, so for the Grassmannian cluster algebra is a cluster algebra defined by this particular quiver. So, and it's been over 20 years. So they first were introduced by Fomin and Zelevinsky, and there's a nice book by Fomin, Lauren Williams, and Zelevinsky. And I really love this slide which I stole from beautiful lectures by Lara Bossinger that she gave at Harvard last 2 weeks ago. So it reminds some of you, reminds us that cluster algebra is a huge subject in mathematics. It has their own classification number. So it appears in all sorts of areas in topology, geometry, combinatorics, number theory. So we are somewhere here now with our applications of cluster algebras. Okay, great. So very good. So we've learned that somebody had to do the calculation of the amplitude amplitudes calculations, obtain the alphabet, and then observe that the alphabet you get is described by the cluster algebra. So let me just review one more time for this particular two examples what it is. For 6 points, the relevant cluster algebra is GR for 6. The quiver looks like that. So you start with this initial seed. It's very algorithmic. You do all the mutation that were defined on the previous slide, and you obtain your cluster algebra variables, which will match the symbol alphabet that I had on the previous slide. So then you repeat this for the 7 points. That's the quiver that describes the Grassmannian cluster algebra for 7 points. You start with this. This is your initial seed. You do the mutations. You get your list, and you obtain your 49 cluster variables. So you do 2 independent calculations. Somebody does the amplitude calculations, and then we do the cluster variable calculation, and they match. Okay, so the conjecture was based on the just 2 loop 6 and 7 point evidence, but this, as you know from Lance, you'll hear more. Yeah, I think that might be the most highest loop I don't know if it's true, highest loop calculation to date. So based on the fact that that if you start with a symbol alphabet described by those letters, you can go and bootstrap, well, Lance and collaborators, many collaborators, some of them are in the audience, we're able to bootstrap the amplitudes up to 8 loops for 6 points and 7 loops for 6 points, 8 loops, and 7 points, 4 loops, using the bootstrap program that I think you'll hear about more. And there's, based on various assumptions, remarkably, they were able to find the unique answer. So there's probably the highest, is that the highest possible loop computation to date? Do you, okay. Okay, but for function, the final answers, okay, but for 6 and 7 points, okay. Very good, so it's very important. So obviously it's very important to understand what the alphabet is and what the assumption going in there. And yeah, so what happens for higher points, the natural question you might ask. And then it's also, there's been a lot of progress there. So starting at 8 points, the cluster algebra becomes infinite, and some symbol letters become, also this is due to the work of Seoul group, the cluster coordinates start involving not just flukers, but square roots. But there's a very nice way to understand those square roots, and the simplest one, and it's been known in mathematics for 10 years, how to think about these square roots. So you usually, in the situations like GR for 8, you would have a quiver with double arrows. And then if you mutate infinite, so it goes back and forth, and there's a certain limit you take, and those square roots start appearing. So I think that's the cleanest way to see those square roots, which is again known, has been known in mathematics, and indeed that's been applied by James Drummond and Omer Gudagan and their collaborators. Actually, this is my very first PhD student also. Chris Galusius participated in this. So they were able to exactly get all the square roots. All right, so that's a review of n equals 4. And, I've been giving this talks for past 10 years. This is great, lots of progress, many things on both sides, on the side of mathematics and the side of physics. But the exciting part is, so I'm really excited about this paper now, because finally, everybody's been complaining, oh, it's n equals 4, why you get some physical thing? Yeah, I've been getting a lot of crap for working in n equals 4. So now, let me tell you, I'll be honest, because I talk to people outside the field, and sometimes I give a colloquium. Some people, okay, but now this is going to be not n equals to 4. So let me tell you a little bit about non n equals to 4. Very exciting. Okay, so the first excitement for us came with a paper by Chicherin and Papathanassiou 5 years ago, and then recently it's been generalized to 3 loops by Papathanassiou and a student who's also here, who's been very excited and missed my talk. Okay, so they found the cluster algebras. He was here. So since August, we actually been very excited by their paper. They found the cluster algebra structure in Feynman integrals relevant to QCD. Okay, not just n equals 4, but these are the integrals, and they find A2, C2, and G2 cluster algebra. So this up to this order, the symbol alphabet for these integrals has been worked out in the paper by Johannes and his group. So you can again take the alphabet and try to match. So the idea is somebody has to do the hard calculation, and then you go and you try to explore, can I match, can I find the cluster algebra? And indeed, the answer is yes. So these are the results for 1, 2, 3 loops, and the algebras are A2, C2, G2. So what are these algebras? I defined for you Grassmannian cluster algebra. So now, what are these algebras? So there's it's 2 stands for 2 initial variables, A1 and A2, and then you perform mutations. So now you cannot draw it as a quiver, but you define the mutation rules in this way, where L is 1, 2, 3, and that corresponds to the A2, C2, and G2. So you do this, and remarkably, so for each case you get, so for A2 you get 5 variables, for C2 you get 6 variables, for G2 you get 8 variables. And then remarkably, if you then compare that with the symbol alphabet that for the integrals that Johannes et al. Computed, there's a match. So that's that was the first example of something beyond of relevance of cluster algebra beyond the. Oh, there you are. Yeah. Okay. I didn't miss my talk. All right. Yeah, that was the first. Probably, I think you do the. Maybe he'll give a gong show on this. So this was the first exciting results of applying cluster algebras beyond the n equals 4. Okay, so, but of course, one of the reasons we're doing it, we want to do something useful for QCD. So so I'll talk about 2 loop, 5 and 6 points massless QCD. So over the years, we've been it's been more and more work by Johannes and his group, and more work over the series of 10 years. We've been paying attention to all the letters, but nothing really has been, we've been paying attention, but not really being able to analyze the structure. But okay, so the full alphabet has been known for quite a while now, and it's given by the, so I just wrote some of these letters. It's given by 25 letters in black, 1 letter green square root in the planar case, and in the non-planar case, there are these extra 5. So that's a summary of the alphabet. So what's the relevance? So it turns out that these letters were shown to coincide with those from a construction based on D4 cluster algebra, but not exactly the variables, because D4 has 22 cluster variables. But of course, there's some other things you need to do to get to 31. So there has been this paper by Bossinger, Drummond, and a student. Yeah. So what I'm going to do today, and this is what we did in the paper yesterday, we are going to construct these letters and the letters for the 6 points from a different but equivalent way, making use of the recent work by Lara Bossinger and Jiarong Li, where they talked about flat cluster algebras. So flat cluster algebras has also been known in mathematics for many years. I'll have a reference on the next slide. But they presented an embedding of, I will define also what it is, of a partial flag variety, F2n minus 2n into the Grassmannian. So that's the result of their paper. And this embedding respects the cluster algebra. So the relevant cases for 5 and 6 points is going to be F235 embedded in G36. So these are the Grassmannian, and F246 into G48. Okay, so now one slide. So it's been known, the flat cluster algebra has been known in mathematics for, again, over 20 years. So the partial flag variety is a generalization of Grassmannian. So Grassmannian is, vector space. So Grassmannian Kn is the vector space dimension K embedded in Cn. And now the flag variety is the following embedding of embeddings. And again, so this variety has a cluster algebra, and it's been known for some time. I will draw a quiver in a second. But so an important thing is that there's an isomorphism between the spin helicity variables. So we will have to match the variables, the angular and square brackets. We have to match those variables into the elements in the partial flag variety. And that map is given by a formula right here. And so that map induces, a map, an embedding between F and G. Okay, I'm rushing now. But here is more detail. So for example, for 5 points, here is the so for F235, there is the initial quiver. So now I told you everything you need to know. Here's the initial quiver. You go and you put it on the computer. You know the mutation rules, and you get your cluster variables. And indeed, in this case, the cluster algebra is D4. It just happens to be isomorphic, and these are the variables. Okay, so now, you were like, okay, but this is 22, but I just told you they are 31. What do you do? Well, in our paper, we showed that you have to do something else. You have to basically, the set of letters that you obtain is not closed under the cyclic group. I goes to I plus 1. So if we take the union, you get exactly all the letters except for this square root, which drops out. So you get 30 letters, 25 planar and 5 non-planar. So, but it's a very clean and easy way to get those letters. Okay, very good. So once we understand 5 points, we can move to 6. So remarkably, the full symbol alphabet has been worked out only recently by several people who I just met. Antonella, whose PhD thesis, I think, was this computation, heroic computation. And she that I also just met yesterday, and Yang Zhang. So, and parallel work by Abru and collaborators. So there's an answer there. Okay, so heroic computations had to be done. Now we can go and see if we can understand the mathematical structure of the answer. So, but first, somebody has to work out. I just want to emphasize over and over again, it's very important to do this very hard computations and spend maybe years sometimes to do these computations, because otherwise we're not able to make any statements. Okay, so so there's an answer. Now, what is the relevant cluster algebra is F46, and that's the quiver. Okay, so that again, you can look it up in our paper. You have the quiver, you know the mutation rule. You go, and Hichen goes and produces the list for you, and Andrzej goes, produces checks, cross checks. So okay, you have a list. So what is the result? Okay, so the result you take. So the actual letters, there are 245 symbol letters. Okay, so now we were able to get all but 36. Okay, so I remain optimistic. So there are infinitely many in GR48. So I remain optimistic. Nevertheless, we made the decision to post the paper with what we had, because it's still a lot that we were able to reproduce. So let me just say a few words. So 7 of these are analog of square root. 135 are these cluster variables. Those algebraic, the 40 algebraic, we got them from infinite. Well, not we, Chen and Andrzej, got them from infinite mutation sequences. Now, some of them start appearing only at order epsilon. Okay, so 27. So these remain mysterious. Okay, so this we're still working on last slide. And so then we would say, okay, maybe they drop out of the amplitude. That's not right. So if you look at all plus amplitudes, 24 of them appear in Yang Zhang and Johannes' paper. So that's the statement. Okay. Now, let me conclude. So I will conclude by just posting you the abstract. So on one hand, the full 245 letter alphabet for all planar massless 2-loop 6-point integrals have been recently determined, very recent work in physics by lots of people doing very hard computation. On the other hand, in a parallel development in mathematics, it's very important to pay attention to what is happening in mathematics. So there's really, again, realization of how important the cross communication is. That there is a cluster algebra preserving embedding of the partial flag variety into the Grassmannian. Okay, so now we just connect the two. So we work out the variables there and compare with the alphabet. Okay, boom. So a few things, a few comments about the results. So missing letters. I remain maybe most optimistic that we will find them by certain C2 mutations, but I think Yi-Cheng, okay, you know, in the coffee break, he said no. The other way, the other way, but right now he said okay. So I personally think there will be some way we will get, oh, okay. Okay, yes, and this is work in progress. So once that's sorted out, there are many things to do. You heard from Ruth's beautiful talk already. There are, so I just talked about alphabet as a whole, but there are many various detailed properties of that alphabet. For example, cluster adjacency, then you go to cluster functions. So it would be very interesting. All of that program that's been done for n equals 4 is very important to redo and understand for these examples. So adjacency, then cluster functions. Then you'll probably hear Matteo Parisi should be here. He'll tell you about the recent nice work on the amplitude hadron tilings. So that's another way cluster algebra plays a role there. So it's very important to take the momentum space amplitude hadron and understand how things work there. And finally, it's very, very important to get more data. So for example, one data is already available here is the prediction for 56 extra letters for 3-loop 5-point alphabet. So it's important we will analyze it once it's available. All right, so that I think concludes the main part of my talk. Yeah, thank you. Oh, no. I would like to also draw your attention and make an advertisement for some of these developments have been remarkable in the past 15 years. So due to Johannes, we are going to have the meeting, Symbology at 15, in December in Max Planck Institute for Physics. Yeah, so please register and attend. Yeah, so I think I'll stop.